We're going to talk about gas exchange in this video. And remember that we have external respiration as well as internal respiration. So this is primarily external respiration. And so this is looking at the movement of oxygen and carbon dioxide from the inside of your lungs into your capillaries. This gas exchange is actually passive diffusion. What does that mean? That means that gases go from a higher to a lower concentration, hence the diffusion part. Passive means that it doesn't take energy. So gases move from a higher to a lower concentration. This is with their concentration gradient. You might have learned in previous biology classes that diffusion will occur even in non-living systems, right? So like, for example, when you put a piece of, or you put salt in a glass of water, the salt molecules will diffuse outward until they are equally distributed in your glass of water. So diffusion doesn't require living systems. And the other interesting thing is that we have designed it so our lungs are capable of utilizing diffusion as a mechanism for getting oxygen and getting rid of CO2 so that it doesn't require energy. We don't want to pump the gases. We don't want to use ATP to pump gases across a membrane. We want to design, we have a design, physiological design that is energetically efficient. So the diffusion of gases depends upon their concentration, and this is what we call the partial pressure. Of a gas is its concentration. So you'll remember that the pressure has to do with the movement of molecules in the atmosphere, and it is measured in millimeters of mercury. And the partial pressure is which is exerted by each gas. So oxygen has a particular partial pressure, as does carbon dioxide have a particular partial pressure, as does water has a particular partial pressure. And then that makes up the entire atmospheric pressure, which at sea level and standard environmental conditions is about 760 millimeters of mercury. So if we look at these partial pressures again, it is actually just the percentage. So if we take 760 and if the approximate percentage is 78.6, we would just times that. So we take 78.6 times 760, and what do we get? 597 millimeters of mercury. 21% of 760 is about 159 millimeters of mercury. Okay, so this is just a percentage. You'll notice that these partial pressures are different when we look at them from the atmosphere to the alveoli. And that is because when we breathe in air, some of the air stays within the alveoli. Remember, we have these lungs that are buried, the respiratory tissue, respiratory membrane is buried deep in the lungs. The function of that is to primarily prevent water loss, right? So we humidify our air. If our respiratory membrane was like right on the surface of our neck, it would dry out, right? So we have these lungs, and we also have a very large surface area, much larger than just the surface area of our neck, right? So let's look at a formula that determines the rate of diffusion. So the rate of diffusion can be described by what I'm going to call Fick's law. So Fick's law is rate of diffusion is equal to big D, and I'll explain what that means in a minute, times surface area times delta P, which is partial pressure, over little d. the difference in partial pressures actually. Okay, so definition, D is a constant, big D is a constant. You do not need to worry about this. This is just the constant of like the simple squamous epithelial tissue in your alveoli. SA is your surface area. Delta P is the difference across the membrane. So it's the difference in the partial pressures across a membrane. And I ran out of room here. And so little d is the distance over which diffusion has to take place. Okay, so let's look at this formula. If surface area increases, so if I have an increase in the surface area, that is going to increase my rate of diffusion. So by having large surface area, I am going to have a higher ability, a greater ability to obtain oxygen and get rid of CO2. If my surface area decreases for whatever, perhaps my lungs, I have illness in my lungs, I have cancer, I have lung cancer, or I have emphysema, which is the collapsing of the alveoli, then my surface area is going to decrease. Okay. My little d is the distance. So that is actually inversely proportionate. So my little d, if my little d increases so that the respiratory membrane becomes thicker, that's going to decrease my rate of diffusion. So emphysema sometimes is characterized by a thickening of the respiratory membrane, and then diffusion is not going to occur as efficiently. And then this delta P, if that increases, the difference between the inside of the alveoli and my capillaries, for example, if there's a great difference in the concentration of gases like oxygen or CO2, then that is going to speed up the rate at which they travel over the membrane. So sometimes this partial pressure, I'll write this, the delta partial pressure of oxygen, right? And then this is the difference in the partial pressure of CO2. So you'll see that oxygen and carbon dioxide. So let's look at the air that we take into our lungs. So we have 160 millimeters of mercury in the inspired air. In the alveoli of the lungs, we have about 104. So there's less concentration of oxygen. There's much greater concentration in the inside of our lungs, right? In terms of CO2, right? So in the alveoli, sometimes they call that dead air. The dead air space in your alveoli is that you haven't gotten rid of all of the unoxygenated and carbon dioxide rich air because you're breathing too shallowly. Okay, so let's look at this diagram right here. This one's really important because it has to do with blood entering the alveoli. Let's go back to this one, sorry. Blood, inspired air. I guess this would be like in the capillaries. So this would actually be in my capillaries. So you'll notice that the partial pressure is greater in the air. So which way is oxygen going to diffuse? It is going to go from the air. Oops. It's going to go from the air into the capillaries. Right? So oxygen is going to move in that direction because it is of a higher concentration in the air than it is in the capillaries. Okay, CO2 is going to move in the opposite direction. So CO2 would move from the capillaries out into the, when we breathe it out. So CO2 moves the other direction. And if that difference in pressures goes to 0, then diffusion will stop. Okay, now let's look at it The internal respiration is when we are moving oxygen into the tissues. And so blood moving in and entering the tissues has a partial pressure of oxygen of 100 millimeters of mercury. And then the tissues, it's less than 40. So oxygen is going to diffuse passively from the blood and into the tissues. Likewise, CO2 is going to move the other way. So CO2 would be 45 versus 40, and so it's still going to leave the tissues. So that passive diffusion has to do with the difference in partial pressures. So what happens when your lungs become diseased, like with emphysema? We can look at an image of this. So this is a lung, normal lung tissue under an electron microscope. And so it's a greater magnification than you would see if you were looking at a light microscope. And this would be the lung with emphysema. So you'll notice that there is much less surface area because some of the alveoli have collapsed and then become expanded. This has a much larger surface area. You'll also notice that the D, the little d, the diameter or the distance over which diffusion has to take place has gotten thicker. So that's going to decrease your diffusion rate. So what could you do for a person who has emphysema? One thing you could do is you could put them on a ventilator and you can give them supplemental oxygen. So if if this decreases and this decreases, one way to increase this is to change this, right? So that's when people get oxygen tanks that they carry around with themselves, because I'm increasing the amount of oxygen that they're taking in their air so that their rate of diffusion stays high enough to support their movement and their activities and their basic metabolic rate, right? Even if this is become thick, increased, and this has decreased. And so ventilators sometimes use the increase in oxygen in order to get more oxygen into the blood.